Hello everyone. I'm going to present to you the findings of an RFCS funded project called Progress, Provisions for Greater Reuse of Steel Structures, which ended back in 2020. This project addressed both the construction and reuse of existing single-story buildings and how new single-story buildings can be designed, constructed, and documented to facilitate future reuse. Why did we mainly focus on single-story buildings? We found that these type of buildings are particularly attractive for reclaiming structural steel because they typically lack fireproofing, meaning that we don't need to remove intumescent painting. They use dry and lean construction systems, and that facilitates the deconstruction in the sense that members are visually exposed. The structural type is also of the repetitive approach, and it can be easily disassembled because connections are mainly bolted connections, and therefore we can reassemble the members at a later stage in a new building. Although the project looked at different levels of structural reuse, either the constituent products, so at individual members, structural component, such as a truss system that you can see here in this system, or even a sandwich panel, and the entire structure of part of it, like specific base from an existing building. In this paper, we mainly looked at the reuse of individual members, so at constituent product level. We also limited the scope of physical reuse to buildings that have been erected after 1970, and also to building structures that is never breaches, because we need to preclude any fatigue loading history. We also only consider damage-free building structures, that is, buildings that have never been subjected to any extreme event limit states, such as fire, a seismic event, etc. Also, we need to be careful about corrosion. Members that are to be reused cannot have accelerated localized corrosion, as it reduces the section, and therefore we can't accept those. Also, in terms of the length to be recovered, the single-story buildings allow long members to be reclaimed, and that's also a positive aspect because we have more design freedom than if we are restricted to short span members. So the overall process for reclaiming steelwork is summarized in this flowchart. So we start by identifying buildings from which we can reclaim steel. We carry out the pre-construction audit that will allow us to answer the question whether steel can be reused or not. If not, then we demolish the building and send the steel to scrap for recycling. If we can reuse, and that follows a whole field survey, the condition evaluation, etc., we deconstruct the building, we batch and label all the members, and then they are transported and reconditioning for use then in design. I have a note here in terms of the storage. We have to bear in mind that usually reclaimed steel comes with a protective coating for corrosion. We need to obviously assess whether there is compatibility between these old coatings and new coating systems, or if, on the other hand, we have to remove the entire coating system from the reclaimed steel. This paper focused on these aspects, whether we can ascertain if the steel can be reused or not, and then we'll focus also on design aspects. In terms of design, we find that we have identified the relevant barriers for design. And we have to ensure, because reclaimed steel, unlike new steel, virgin steel, come with a mill certificate. So we are able to identify all the properties to be used in design, and we are also able to trace the steel to a specific inspection document. Well, reclaimed steel rarely comes with those mill certificates. Um, so we need to ensure that reclaimed steel satisfies both performance requirements, so mechanical, physical, and dimensional properties, as well as the quality requirements from nominal specifications. This will help us ensure that we can use in designs to the Eurocode suits. Obviously, as all structures, the structures made from reclaimed steel also need continuing integrity. So in terms of the material, the execution norm 1090 part 2 allows us to use non-conforming steel as long as we characterize a number of properties. Compulsory are strength, elongation and tolerances on dimension and shape, and the heat treatment delivery condition, which is relevant for hollow sections. Strength can be easily determined by means of tensile testing or simple non-destructive testing like a hardness testing, which allows you to correlate the hardness to the yield strength of the material. Tensile testing obviously are destructive testing procedures and allow you to characterize the full mechanical behavior of the steel. Other properties are required, if required, need to be determined, like, for example, impact strength or toughness, the through thickness requirements for the Z quality, etc. In addition to this, if the steel is to be welded, the chemical composition needs to be declared as well. And that can be done by, for example, XRF spectrometer, so for the chemical analysis of the steel, but there are other ways. The second aspect of the classification is for reliability assessment. So we've looked at the mechanical and geometrical properties, but we also need to look for product conformity, quality, and traceability. And this means that we need a mill certificate, or we need to recertify the steel, because we need to ensure that the steel meets all the relevant material specifications. So if we think about new steel, we are thinking about perhaps 10025, and also the reliability requirements for the design to Eurocodes. Otherwise, we need to test the steel and show that it meets all the requirements. In terms of identification of the steel grade, in this project we proposed to use the guidelines from another RFCS project, Safe Brick Tile project, which characterized a number of steel grades and identified the boundaries of properties to classify a steel to a specific grade. These guidelines will be included in a new annex in the revised Part 1.1 of Eurocode 3. So finally, we proposed 3 classes for reclaimed steel, A, B, and C. Class A, we have the original mill certificates, and the only thing we need to do is to ensure that the steel conforms to the existing mill certificate. So we carry out, say, a minimum of non-destructive testing, and the original certification is still valid. Class B materials, we don't have the original material test certificates, and therefore we need to carry out material testing according to a protocol I'll show you later that was developed at the SCI as a side to this project. In this case, for adequacy, we need to test the steel, and then we need to recertify it. Both Class A and B will allow for CE marking of the fabricated structural steelwork. Class C remains for unidentified steel. That means that in the case of non-safety critical structures, such as agricultural buildings, for example, you can perhaps consider using Class C materials if it doesn't allow for CE marking, and in that case you would adopt the most conservative steel grade in accordance with structure age and location of the building from where you reclaim the steel. So this was the protocol I was referring to, which was developed at the SCI, and basically it contains guidelines for sampling, where to sample the materials, how to group structural members in order to make a statistical evaluation of results. And we consider the destructive testing as for new steel, say, per batches of 20 tons. Once you have sampled, you would test the material in order to specify mechanical and chemical properties in the case of Class B materials. And according to the consequence class of your building, the one you're designing, you find guidelines in this protocol how to select, or the number of coupons that you need to select for each test unit, etc. So the protocol considers for Class A then only non-destructive testing. For example, in order to identify the steel grade, the steel grade, you can use the hardness testing. For Class B, you will need to carry out, in addition to the non-destructive testing, tensile testing in order to fully characterize the mechanical properties. And for Class C, you won't require, as it remains unidentified steel. However, bear in mind that if you want the steel to be welded, you always need to determine the chemical composition. Now, looking at some design aspects, so this flowchart summarizes the Eurocode approach to design. So you start with the structural idealization. You need the design values for geometrical data and the characteristic values for material properties. We've covered that in the slides before. Also, you need to represent the actions and select the correct partial factors for the use in design. In terms of partial factors for the material, so for resistance, we expect the reclaimed steel members to perform as identical to new steel. So we are proposing to use the same gamma M0, so the partial factor for resistance of sections, and the partial factor for resistance to fracture, the same as the Eurocode. Please note that the 1.1 is a specific UK value. Typically, this is 125 according to the SEN proposed values. This is the national annex in the UK. For buckling, however, we have derived following a reliability analysis, and these details can be found in the paper. We have proposed an increase to the gamma M1 for stability calculations, and an increase of 15% to the value originally proposed in Eurocode 3. As I said, the details of this derivation can be found in the paper. For actions, we have two possibilities here. Either you carry out business as usual, or you can. We also consider the fact that when you are upgrading an existing structure, as long as the human safety levels are not exceeded, you can consider designing for a shorter design life. So, for example, if you're going to design for 30 years and compensate for a slight lower partial factor by high level of quality management and control, you need to check Eurocode 0. You may consider lowering to a consequence class 1, but in that case, the proposal is to use equation 610 from Eurocode 0 instead of 610A and 610B, as this leads to a higher reliability index. Some final remarks. We can conclude from this work, steel buildings can be dismantled like a kit of parts at the end of their life. So this is an attribute of steel structures, and in particular the single-story framed buildings that we looked at. And it's possible to actually reuse steel from those buildings instead of melting and use it for scrap and produce new and produce primary material again. Some issues were raised during the project, such as material integrity, properties, and CE marking. We found a way to overcome most of these issues, and we showed that it's still possible to design to Eurocode 3 by only considering only two aspects. We propose to restrict to elastic global analysis, so we wouldn't consider plastic global analysis with reclaimed steel members. And for reliability, we propose to modify the partial factor gamma M1 for stability calculations, and consider the possibility of, as well, of using lower partial factors for actions. This concludes my presentation. Thank you.